Hello, in this video we introduce yet another type of equation to solve, absolute value equations and inequalities. Let's get started. So what do we mean by absolute value? Most people, when they hear or see absolute value, those bars, right, and then a number inside, they instinctively know what to do. But did they really know what it means? For example, if you see here the absolute value of a number like 3, you would know that the answer would be 3. Or if I said the absolute value of -3, you would say 3. But what is it saying? The definition of the absolute value is the distance from that number to 0 on the number line. So if you say the absolute value of 3, what you're really saying is what numbers are 3 away from 0, okay? So that would be 3. But if you put -3, how far is that from 0? Also 3, just in the other direction. Formally speaking, you can see in the box on the side here, absolute value of x is defined to be the number itself, x, as long as the number is 0 or higher. So like 3, it was 0 or higher, so you kept it the way it was. Or negative x, and that just means the opposite of the number, whenever x is less than 0. So whenever x is negative, whenever the absolute value of the number has a negative inside, you simply take the opposite, you make it positive. So that's what we actually mean formally by the absolute value function. So what do you do if you have an equation now where instead of the absolute value of a number, you have the absolute value of a variable like x? What do you do? So in an absolute value equation like that, the first thing to notice is that this is actually representing a graph. We're going to be studying this graph later in the semester. It turns out that this equation, let me grab a pen, the equation y equals the square root of x, it will actually end up, when you plot all the different possibilities, it ends up really cool. It looks like something like this. The absolute value of 0 is 0, the absolute value of 1 is 1, but the absolute value of -1 is also 1. The absolute value of 2 is 2. The absolute value of -2 is also 2. And notice that we're forming two lines, right? Two different pieces, a piecewise graph. We'll talk more about that later in the course. So it turns out if you play connect the dots, you would get a V-shaped graph. Okay, so if you were graphing the absolute value function, that's what ends up happening. So as far as finding the two different possibilities, you consider two cases. The first case, well, whatever's inside there could equal the positive number. So for example, we have the problem, the absolute value of x equals 3. So we're asked to find what possible values for x could make this true. You might already know the answers, +3 and -3. So what did we really do? We said we take what's underneath there, x, and we set it equal to the positive version. So set x equal to +3. That's one of our answers. So now we know that 3 is one of the numbers that is 3 away from 0. Okay? What's another number that's 3 away from 0? Well, that would be -3, wouldn't it? So that's by taking what's inside the absolute value bars and setting it equal to the negative version of the number. So x equals -3, and that gives us our second answer. And you can read the details of that slide for your own enjoyment until you really understand the process there. Now, if it was always that easy, the absolute value of x equals a number, so I make it x equal the positive or the negative number, there wouldn't be a whole point of having a video, would there? Okay? But it gets a little more complicated because sometimes inside of that absolute value, those absolute value bars, we have more complicated expressions than just x. So we need to know the protocol, and the protocol will be case 1, make whatever's inside there equal to the positive number on the right, and then case 2, make whatever's inside there equal to the negative version. So let's see an example on the next slide of doing just that. Solving absolute value equations. So the one that I have in your notes, so if you actually have your slide pulled up, it should say something like this, for example. It should say 2 times the absolute value of x plus 1 equals 4. Okay, that's a lot more complicated than the absolute value of x equals 3, right? So you might be thinking, why do math teachers always do this? They show us an easy example and then we see something much harder. Okay, that's exactly what happens, I know. But here is the idea here. We are going to isolate the absolute value part first. Oops, first. So to do that, what is the absolute value part in this problem? That's right, it's the absolute value of x plus 1. So how would you isolate? Well, you'd have to undo whatever's next to it, right? What's the operation that's connecting the 2 with the absolute value of x plus 1? Next to means multiply, so that's the juxtaposition. When they're next to each other, we assume that's multiplication. How do you undo multiplication? That's right, you divide. So if I wanted to isolate the absolute value part, just like we do with square root equations, same idea, or even later on with exponential equations, we divide both sides by whatever's touching it. So dividing both sides by 2, I now have that the absolute value of x plus 1 equals 4 divided by 2, which is just 2. So you've done step 1. You've isolated the absolute value part. The absolute value now is equal to 2. What is this really saying? Well, it's saying that the absolute value of some number plus 1 has to be 2 away from 0. In other words, the distance away from 1 to this number is 2 in both directions. So let's see if we can figure out what those numbers could be. Well, how do we do it? We take what's in the absolute value bars. This is the new part, right? X plus 1, and we say it could either come from equaling negative 2 or positive 2, because when you take the absolute value, that's how you get 2, right? So here's what we do. We solve two equations using both the positive and the negative outcome. So either x plus 1 equals positive 2, or x plus 1 would have to have equaled negative 2. Either way, taking the absolute value of the result gives you 2, doesn't it? So let's see what happens now. We can solve these linear equations by undoing addition and subtraction. With subtraction, I should say. So when you subtract 1 from both sides now, what are your two answers? Either x equals, the ones cancel, death to you, death to you. 2 minus 1 is positive 1, my bad. So 2 minus 1 is positive 1, or death to you, x equals negative 2 minus 1, which is negative 3. So what does that mean? Well, if you were to plug them back into the original equation, they should make the equation true. In other words, both sides should say the same thing. So if I put in a 1 there, 1 plus 1 is 2, and 2 times, well, the absolute value is 2 is 2. 2 times 2 is 4. If you put negative 3 inside there for x, negative 3 plus 1 is negative 2. Absolute value of negative 2, 2. 2 times 2, 4. So in fact, our two answers are negative 3 and 1. And if you were to look at the graph on Desmos, you would see that these are indicating for you your x-intercepts for that absolute value graph. Okay, so that's what that's telling us. Okay, so we've now shown you how, step by step, to attack, or to approach, I should say, nicer, to approach an absolute value equation. Notice here what you did not do. You did not simply move the 1 to the other side when it's trapped right here, right? You can't move 1 yet until you separate into two different possibilities, either the positive 2 or the negative 2. Okay, let's take a look at another example, and again, always feel free to pause and practice on your own and see how you did. Example 1 says, find the real solutions, if any, sometimes there are no solutions, for this equation. So first step of problem solving, identify the type of problem you're dealing with so that you can pick the right tool to solve it. So what type of problem is this? It's an equation which has absolute value bars. What do we do in that case? We isolate the absolute value bars. Already been done because there's no number in front to divide by. And then we say, what are the two possible outcomes? Or in other words, what possible inputs inside the brackets here, I should say, absolute value brackets, what possible inputs would produce a 2? Well, either a negative 2 or a positive 2. So that's what we do. We say what's inside must either equal negative 2 or a positive 2. Negative 2 or a positive 2. So if you're asking yourself, Professor, will I always have to do this? Yes. Anytime you see an absolute value bar equation, that's what we do. Isolate it by dividing if there's a number in front on both sides, and then set it equal to the two possibilities. Where did it come from? Negative or positive 2. In this case, solve those linear equations. You can feel free to pause and do it on your own. See how you did? Did you add 1 to both sides here and get that 3x must equal negative 2 plus 1, which is negative 1? And on the other equation, adding 1 to both sides would give you that 3x equals 2 plus 1, which is 3. So what were your two answers for x? That's right, x would either equal negative 1/3 or 1. That's right. So again, if this was a Desmos graph or a graph of the absolute value function, those are the two x-intercepts because it's basically setting it equal to 0 and solving. So feel free to check those out. You could also input them back into the original equation to check whether or not your problem solving worked, right? If you plug in negative 1/3 and multiply it by 3, you get negative 1, and negative 1 minus 1 is negative 2, whose absolute value is 2. Similarly, 1 does the same thing. You'll get 3 minus 1, which is 2, and his absolute value is 2 as well. So we've demonstrated now with a few examples how to solve equations that have absolute value bars. The next thing I'd like to do is introduce the idea of solving an inequality, right? Inequalities could be less than or greater than, less than or equal to, greater than or equal to. In each of those cases, you're not going to find specific answers like x just equals this number. Rather, you're going to find a slew of possibilities. X could be any number bigger than 5 or any number less than negative 4, something like that. So we're going to have to be very careful to first identify the situation and then apply the appropriate result tool. So let's take a look at our possibilities here. When we see an inequality symbol with absolute value, so you have to see both an absolute value situation along with an inequality situation. What are my inequalities? Less than, greater than, less than or equal to, greater than or equal to. If I see any of those 4 inequality symbols along with absolute value bars, that should trigger a certain procedure to follow, because here's the understanding behind it. We know, for example, we had one earlier where we had an equation where the absolute value of x equaled 3. In that case, we said that the only possible answers were that x equaled -3 or x equaled +3. And those were our 2 solutions, right? Our solutions were -3 or +3 in that situation. But what about below it on the left? We see the absolute value of x is greater than or equal to 3. So what is that saying? Instead of saying we need to find the x values which are exactly 3 units away from 0, in which case we got -3 and 3, it's now saying we need to find any x value which is at least 3 units away from 0, 3 or more. That's what greater than or equal to 3 means, 3 or more, equal to 3 or more than 3. So look at what that means on our graph here. Below in the number line, you have a 0 in the middle. If you go out to the right 3 units, starting there and to the right, that's what we talk about when we mean greater than or equal to 3. But notice that's not the only way we could interpret absolute value, right? Because it's in either direction, 3 or more away. So it could also be going out to the left, -3 and beyond, right? So -3 and beyond. So that would be less than -3 or equal to -3. How would I write that solution in what we call interval notation, since there's a whole interval of numbers? Well, we could say -infinity with a parentheses, up until -3 with a bracket. This U means union symbol in set theory, which is a symbol that we use to say or. So this or this is where our solutions could be. So in that region, anything starting at -3 and to the left, or starting at +3, comma, approaching infinity with parentheses. So anything starting at 3 toward infinity means getting bigger and bigger, more and more to the right. Remember, we use brackets if we're including the endpoint, and we use parentheses if we're not including. So one is inclusive and one is exclusive. Now notice this is going to be almost identical to the box right below it. Absolute value of x is greater than 3. So what is that saying? We need to find all x values which are more than 3 units from 0 in either direction, because it's absolute value, right? So it's bigger than 3 or less than -3. That's exactly it. So notice on the picture here, we had open circles because we're not including the 3 itself, right? It was strictly greater than 3 units away. So anything bigger than +3, anything less than -3. So in interval notation, that would read -infinity, comma, with parentheses for the infinity symbol, -3 with a parentheses, since we're not including the -3 itself, or starting at any unit to the right of 3, parentheses 3, comma, infinity, parentheses. So notice those 2 types of problems will be an identical approach. You'll simply take whatever is inside the absolute value bar and say it must be either bigger than the positive number or less than the negative version of the number. Okay, so that's always going to be our approach for greater than or equal to and greater than absolute value inequalities. So these 2, very similar, okay? I'll switch colors on you here, see if you can still see maybe. I'll do white, okay. So what about less than or equal to, or less than? Well, in those cases, notice what it's saying. The absolute value of x is less than or equal to 3, which means we're saying any x value which is less than or equal to 3 units away from 0. So if 0 is in the middle, 3 units away to the right would be 3, 3 units away to the left would be -3, but it says less than that distance or equal to that distance. Wouldn't that include a 1, a 2, a 3, and a -1, a -2, a -3, and every value in between? It would. So how would I write that answer in interval notation? Well, if it's between these 2 numbers, we're not going toward infinities now, we're saying we're constrained between these numbers, we would say -3 would be my left bound, we'd use brackets to include it because we had the equal to, and 3, +3 would be my right bound with a bracket. So that's going to be extremely similar to the box below it, which says that the absolute value of x is strictly less than 3. Notice there's no equal to now. Saying almost the exact same thing, but the only difference is you can't include 3 and negative 3. So we'd say any numbers between negative 3 and 3 are going to be less than 3 away from 0. So parentheses, negative 3, comma 3 would be our interval notation. So again, extremely similar setup when we have a less than or equal to or a less than with our absolute value inequalities. At this point, I highly recommend pause this video, write down an example for each case, make note cards, make flashcards, so that you really can see the difference, the distinctions between one, what it's saying, and two, what you have to do when you see that certain type of inequality. Okay? So once you're ready, we're going to head into some examples. Example 2 says, can you solve it shouldn't say by there, sorry. Can you solve the following inequality? So solve the inequality and graph the solution set, writing it in interval notation. So what type of inequality is this? Let's identify our problem. That's right, it's an absolute value inequality. So that's one thing, meaning it has a positive and a negative potential. What else do we know? It's greater than. So absolute value means distance from that thing to 0. We want the distance from that thing to 0 to be bigger than 6 away. So if I went to a number line, it's really important when you're trying to problem solve to visualize what's going on. So in a number line situation, if 0 were in the middle, 6 would be somewhere to the right, and negative 6 would be somewhere to the left, equidistant there. And what we're asking you to do is to find all possible entries for x, which would make the absolute value of 2x more than 6 units away from 0. So more than 6 would mean not 6 itself, but anything beyond 6, right? Not negative 6 itself, but anything less than negative 6. So anytime we have a greater to or greater than or equal to symbol, we go beyond those numbers, right? But when it's less than or equal to, between those numbers. That's the distinction. You can write those in your notes if you like. What about parentheses, brackets? Which is it? Good, it's going to be parentheses because we're not including, right? So parentheses opening toward the direction you're going. Now that we know the basic idea of what's going on, what did we do? Well, I like to draw the picture so I can visualize what I'm saying, but also so that I kind of know what to do next. I need to find all potential answers for 2x, which are less than negative 6. So I say 2x must be, less than, I almost said greater than, less than negative 6. So you're thinking, Professor, why did you just flip the arrow? It was greater than. Because it has to be in that region, right? Beyond 6 away means to the left of negative 6, okay, in that context. Or, what's the other option? That 2x, what's underneath, has to be beyond positive 6. So that would be greater than positive 6. So this will always be the setup for greater than or equal to problems. You take what's inside and you set it less than negative or greater than the positive. So at this point, it's a matter of simply solving inequalities, linear inequalities, which are not bad, by isolating for x. Undoing multiplication on both of these, we would get division by 2 in both cases. 2x divided by 2 is just x. And since we didn't divide by negative, but a positive, we keep the sign the way it is. Negative 6 divided by 2 is negative 3. So one possible answer for x is that your x values are below negative 3. They're less than negative 3. The other possibilities for x values, when you divide it by 2, would be that x must be greater than 6 over 2, which is just 3. Well, that kind of makes sense, because if you put in negative 3 for x, you get negative 6, whose absolute value is 6, and we want to be beyond that, so that makes sense that it's less than negative 3. And bigger than 3 makes sense, because if you put 3 in, you'll get 6 again, and we want to be beyond that. So how do we write this in interval notation? Negative infinity to negative 3 with a parentheses, or parentheses 3 toward infinity. So those are the places where our values could potentially come from. If you want to show it on the number line with 0 in the middle, positive 3 on the right, negative 3 on the left, we're talking about the space to the right of 3 for x values and to the left of negative 3, and opening with parentheses since we're not including the negative 3 and the 3 itself, since it didn't have the equal to symbol. Okay, so again, you can make your own examples up like this anytime you have a greater than or equal to symbol. This will always be the game plan. The only difference is brackets versus parentheses. Let's do one more example, but this time it's a little different. Let's clean that up. Okay. It says solve the inequality, graph the solution set, and write in interval notation. We have absolute value of 2x plus 5 being less than or equal to 7. So what do we do first? Well, if there is any isolation, we would do that first, but there's no number in front, so we don't need to isolate. It's already been done for you. The next thing is identify the problem. This is an absolute value situation, which means we have a positive or a negative outcome, potentially giving us 7, right? And then we have less than or equal to. Does that mean beyond or between 7 units from 0? Between. So yep, that's the original setup with 0 in the middle, 7 somewhere to the right, negative 7 somewhere to the left. We always do that with absolute value, go in either direction from 0. But since we have less than or equal to, this time it will be between them. So the distance has to be less than 7. So 0, 1, 2, 3, 4, 5, 6, all of those values work, including 7. So we'd show off with a bracket there. And then any value less than negative 7 would be less than 7 away from 0. So that would include negative 1, negative 2, negative 3, all the way through negative 7. And we again would use brackets because we are allowed to include the endpoint of negative 7 and positive 7. So that's the idea. What x values would produce the absolute value part in that space? So we got to figure that out. So we're going to first take that 2x plus 5. Oops, let me fix that. 2x plus 5 is trapped in between two things. Now, some students like to separate these out as well. So it has to be here and it has to be here and then put them back together again. Personally, if I know I'm trapped between the two numbers, I can simply do this in one step. 2x plus 5 is trapped between 7, so it's less than or equal to 7. I can see that from this perspective. But it's also to the right of negative 7, so it's greater than or equal to negative 7. So from his perspective, he's greater than or equal to negative 7. So we're looking from his perspective. 2x plus 5 is either less than or equal to 7, so what's inside is either less than or equal to 7, or it's greater than or equal to negative 7. Sorry, instead of or, it should be and it's greater than or equal to negative 7. Okay, so now to solve an inequality that's trapped in the middle like this, we want to isolate x in the middle. So the first thing we have to do carefully is to undo the addition before the multiplication. So how do you undo addition? That's right, subtract 5 in every piece, each of the 3 pieces. Well, negative 7 minus 5 is negative 12. In the middle, death to you, we have 2x. And on the right side, 7 minus 5 is in fact 2. One more step and then you'll have your solution to interpret. How do you get x completely by itself when there's multiplication involved? That's right, division. So divide every piece by whatever's touching x. Divide every piece, in this case, by 2. Well, negative 12 divided by 2 is negative 6. And 2 divided by 2 is gone, so that's just x, 1x. And 2 over 2, it's not 0, but 1. So we're getting that x values need to be trapped between negative 6 and positive 1. See if that makes sense. If you put in negative 6 into your original inequality, you'd have 2 times negative 6, which is negative 12, plus 5. Well, negative 12 plus 5 is 7, and we know the absolute value of 7 is 7. What about 1? Well, 1 times 2 is 2, and 2 plus 5 is 5, whose absolute value of 7 is 7. So again, those are both going to produce 7 units away from 0. So we're trapped in between those values. How do we write this, though? Well, on a number line, negative 6 is somewhere here on the left, 0 is somewhere here, and 1 is somewhere here. So what are we really saying? Well, our solution should be between negative 6 and positive 1. And since we're including with the equal sign the endpoints, we would use brackets. So our answer would be bracket negative 6 to 1. Now the only difference here, if this had been a less than 7 situation instead of less than or equal to 7, would be what? That's right, brackets would turn into parentheses. So I've shown you a few examples today of how you can solve equations with absolute value by setting what's inside equal to the positive or the negative and solving. Inequalities, which are greater than or equal to, where we go beyond that distance in the positive and the negative direction. And inequalities that are less than or equal to or less than, where we stay between the two. So some of these will seem easier than others for you. That's why it really is important that you practice and have really clear notes as you're reviewing and practicing so that you understand the game plan in each of these scenarios. All right, it's up to you now. I'll see you next time. And remember, math is not a spectator sport.